moment assume that, so here Bob knows everything about the first set, so he'll say, do nothing to Alice. And Alice is going to XOR her input as 0 with the bits in this set, and XOR her input as 1 with the bits in the other set. So these are keys, we'll use them as a one-time pad, and I guess it's clear because Bob knows this bit here, or the bits in the set, he can then reconstruct as 0. And he knows nothing in here, so because he does not know the key to the one-time pad, he also knows nothing about S1. Say we're in the other case, where Bob knows all the bits in set A, but really he wanted to have her second input, so he'll tell Alice, okay, swap. Note that this does not leak any information because Alice knows nothing about what bit Bob wants to begin with. And then she'll just do the opposite. So she'll use this guy here to encrypt her first input, and she'll use this one to encrypt her second input. And again, because these are keys to a one-time pad, this will all work. So Bob can compute the one he's interested in. So to conclude, I would like to mention, you are probably thinking, this is completely crazy. No quantum computers have been built yet. Maybe it will take another 50 years before we can do so. But I'd like to emphasize that this can actually be done. Of course, there's some practical issues without a quantum computer. So we do not need to implement a quantum computer. Actually, all you need is the same kind of hardware, or maybe improved detectors, that Vadim was talking about yesterday in his talk. In particular, we will also not need to store any quantum information. So we don't need any storage. It's only assumed that if you want to cheat and break the protocol, you need quantum storage to do so. And the goal, of course, say, if you think about this task of identification, is to make this very tiny. Say maybe as big as this laser pointer, where you have some keypads on the laser pointer, and you punch in your pin code, and it will execute this quantum scheme with the machine. Now you may also say, this sounds completely futuristic, but in fact people are working on nanoscale lasers, which could potentially be used for this. So this is not something which is maybe really futuristic, but it can actually be done. So this concludes my talk, and I'm happy to have any questions now, or also, of course, after my talk. I'm still around. Yeah?
Thank you very much.
So in the final step, you have Bob send this information to Alice, but these were the shared bits. Presumably, Bob needs to also XOR that with a random value to prevent Alice from knowing its choice, because Alice does know these bits, so she can compare. So that's what one of your the last slide of the protocol.
Are you saying why I can do the swap operation?
No, I'm saying so they generate these shared bits and then compress them with the hashing, and then Alice has 2 bits. And Bob has 2 bits, except one of them he doesn't know, so he only knows one of them. And he sends that choice or swapped to Alice. But then Alice can compare those. It can see...
Bob does not send the bits to Alice. Maybe this was a bit fast. Let me see where the slide is.
So the key bits.
No, Bob does not send the key bits to Alice, of course. Let's see. How do I... Yeah, I have too many animations in my slides, obviously. Let's see.
Let's skip to the last slide and then go back.
Okay.
Oops, fine.
So let's go back to this slide. And you were wondering, can Alice compare? But note that Bob does not send these guys to Alice. She only tells her whether he wants Alice to do this one, or whether he wants Alice to do this one. But he does not send the key, of course, to Alice. Sorry if that was maybe a bit fast.
Yeah, okay.
Okay.
So, sorry, another stupid question maybe, but you assume that Bob can do anything but store the quantum state longer than a millisecond. Why? This seems to me a little bit arbitrary, just to assume this. Let's say if Bob can do everything but the storage, why do you choose this? I don't really get this.
Why did we choose this assumption? Well, I mean, we choose this assumption because it's kind of realistic, because, like I said, I mean, the best memories today can do 1 millisecond. And the thing is, theoretically, it's easy to think about, it's one approach to think about this as a coding problem. And the reason then when I say he can do anything in advance, what it means is he can perform any error-correcting encoding that's possible. So that's what it means, that he can do anything beforehand. Yeah? Chris, can you give him the microphone? Oh, no? Okay.
Hi. So the assumption that no information is passed from Bob to Alice in the first stage of the protocol, what if Alice has entangled all of the bits that she sends to, all of the qubits that she sends to Bob, and then stores the entangled kind of pair counterparts in her own storage, which is also noisy? She only needs to extract one of those to determine which set Bob's chosen, right?
So, I mean, surely Alice can send entangled qubits to Bob. I mean, it's not all so simple as I have just described. But the intuition is that there's no information coming from Alice to Bob. You want, in some sense, which is a problem in quantum protocols other than in classical protocols, that the protocol is completed at the end, after the final message. And in a quantum case, that's not necessarily the case, because, as you say, maybe Alice sends something entangled, and somewhere 2 years down the road, she's going to measure it. So there are some few things, but it can be addressed. I have not talked about this, but we can talk about it later. No.
Hi. That 1 millisecond, how likely is that to change in the future? Will that become longer for storing quantum information?
Well, surely it will become better to store quantum information. I mean, actually, I certainly hope that eventually there will be some reasonable quantum memories. But note that there are 2 points, in fact, where noise can occur. Already, when I want to convert the state of a photonic qubit into an atomic ensemble, there can be some noise. So even if my memory would in the end be perfect, I would already have some noise. And in fact, by increasing the number of qubits that Alice sends to Bob, one can still obtain security in this setting. Of course, there's some theoretical limitations, but in most cases, this is still possible. I mean, note that here, if I say that Bob can store some k times m qubits, or higher dimensional systems, where m is the number of qubits transmitted from Alice to Bob, and k is some number, say 2, which can be even larger, or a half. The quantum memories that exist today can store a small constant number of qubits. So in fact, in all cases known today, k is 0. So there is no storage that scales for the number of qubits that we transmit. I mean, of course, it's an assumption, but I guess it's a realistic one for a long period of time.
This might be a little silly question, because probably I missed the point, but before you separate into 2 sets, into set A and B, Bob receives an arbitrary number of bits in a correct way, like he knows after he's told the encoding which ones are correct and which ones are incorrect. And then, since Bob doesn't communicate this information back,